Morning, good afternoon, and good evening, depending on your location. Myself, Karthik Vaidyanathan. I'm a computer science postdoctoral researcher at the University of L'Aquila, Italy. This work was done in joint collaboration with Federico Di Menna and Professor Henry Muccini from the University of L'Aquila. Over the years, the complexity of software has increased. The methods to build software has also evolved rapidly. In today's world, if we want to implement a software, as shown here, one can make use of layered architecture, microservices, traditional SOA. Even within microservices, there are hundreds of patterns. Now, once this is decided, the question is what technologies to be used. There are always many options, and most often this is selected by taking into account various factors, including technical features of the language, organizational alignment, and so on. Now, once this is done, the software is developed and deployed. Then the real question comes: how to handle runtime uncertainties or provide guarantees on the quality of service of the software. This question is becoming more and more popular these days, especially in the industry with the plethora of technologies and the increasing complexity of softwares. One solution is to use a self-adaptation mechanism where the system can adapt based on the changing context so as to guarantee the quality of service. The image here shows the famous Merkle loop of self-adaptation. The running software system is the managed system, and to this, a managing system is attached, which performs the 4 different activities. It continuously monitors the managed system, analyzes to check for any issues, plan what needs to be done in case of an issue, and finally executes the plan on the running system to accomplish the adaptation. The 4 activities further share a common knowledge base among them. However, the question that is often not answered clearly is how to implement such a managing system. What kind of architecture needs to be used to implement the managing system to guarantee the goals of the managed system? To contextualize a bit, let us consider a concrete domain. As we all know, we live in a world of Internet of Things. However, architecting IoT system comes with a set of challenges. These challenges relate to the heterogeneity due to the different types of components in an IoT ecosystem, ensuring quality of service, interoperability, and the list goes on. A recent article from Cisco states that around 75% of the self-initiated IoT projects were considered as failures due to the lack of proper software engineering practices. All this can particularly have a big impact on the overall quality of service. 2 such important quality of service challenges in IoT, which are becoming more significant these days, are that devices might run out of battery due to resource constraints. IoT devices are expected to consume around 21% of world's electricity in near future. Second, amount of traffic generated can impact the overall performance of the system. And further, this in fact can have a big impact on the global carbon footprint. Let's put this in perspective. Let us consider a real scenario. So NDR stands for Notte di Ricercatore, is a street science event held at the city of L'Aquila as a part of the European Researchers' Night. It is a one-day event where public and researchers are brought together to share different types of information and entertainment from morning to late night. The image on the left shows the event map of NDR, and the right, what you see in the right is the screenshot of the mobile app, which can be used by the public to locate different events in the city. Now, we have collected some observations from the past editions of the event. First, around 35,000 people attend the event. Then late hours are more crowded than early hours because people returning from the office, they join the event. And weather condition can have an impact on how user selects a venue. It can be an indoor venue or an outdoor venue depending on the weather. Then what happens because of all this, there will be tremendous amount of crowding in the city center. To handle this, our team was invited to create an IoT-based solution for better management of the overall event. However, we had 2 main constraints. One is the limited availability of external power sources, as the event happens in the city center and the availability of power sources are limited. Second, one of the ways to reduce energy consumption is to reduce communication. However, when you reduce the communication to a very low value, it means that you don't have proper service accuracy, so you won't be able to make good decisions. So the question is, how do you minimize energy consumption without minimizing much the service accuracy? So the figure here shows a high-level architecture of the part of the system planned for India. It consists of 2 main services. One is automated parking lot control, which makes use of parking mat sensors in the entrance and exits of the parking lots. These are then sent to the display units and further sent to the user mobile, where they can decide which parking lot to select. The second main service is related to the automated venue control, which makes use of RFID sensors and people counters in the venue entrances and exits. And these data is further used to guide users on the availability inside different venues. But the question that remains still is, what about the constraints? How can the uncertainties be handled related to the energy consumption or related to the service accuracy? To this end, we developed a machine learning driven approach that extends the traditional MAPK loop with a machine learning engine and further supports proactive adaptation of the IoT system. We did implement this approach. However, we had few questions post the implementation. First thing is we implemented it using a kind of layered architecture. And while doing some tweaks, we noticed that when we replaced one of the connector with a message broker, the effectiveness of the adaptation improved. So the question that came into our mind was, what is the optimal way to implement the managing system? The next important question was, what about the quality of service of the managing system? The research on self-adaptation with the community has mostly focused on coming up with approaches for improving the quality of service of the managed system or the running software system. But what about the managing system? And our hypothesis based on our experience was that if the quality of service of the managing system is optimized, and if we can use good approach for performing analysis and planning, then it can improve the quality of service of the managed system or the running software system. So this motivated us to come up with a framework where the overall goal was that given an IoT system and given a set of quality of service goals for the managed system as well as that of the managing system, our goal is to develop a framework which can take into consideration the different implementation options or the strategies as we call for implementing the managing system and further identify an optimal architecture to implement the managing system. Hence, we developed the feast framework. The figure here provides an overview on the feast framework. It follows the standard CBAM approach, which is used for analyzing different architectural decisions with respect to cost and benefits. So the first part of the approach is to define a set of operational scenarios of the managed system or rather the IoT system. During this stage, the quality of service goals of the managed and the managing system are also defined. This is usually done by the architects or other stakeholders. The next step is to define the different candidate architectural strategies or rather implementation architecture for each of the scenarios. Then these implementation strategies are analyzed based on the different quality of service goals. The analysis makes use of simulation and cost benefit function to perform a detailed analysis of different implementation strategies. The evaluations then evaluate the strategies by trading off cost and benefit. It then provides a strategy. If this strategy satisfies the goal, then it is selected. If not, then again, the architect or the stakeholders or the engineers have to go back, define new architectural strategies or modify the strategies and evaluate it again till we get an optimal architecture for implementation. In this way, the framework allows the architects or engineers to systematically select an optimal strategy. In the next slide, we'll provide details on each of the steps. The first stage of the framework is to define the scenarios. In this step, the architect or the engineer defines a set of operational scenarios of the managing system through the scenario definition process. In this process, the architect is responsible for elaborating the different scenarios in which there is a control or a data flow from the managed system to the managing system. For example, one of the possible scenario is that the managing system needs to gather the quality of service from the NDR IoT system every 1 second. So especially in the late hours where it will be more crowded, it needs to make accurate adaptation decisions. So it needs to gather data fast in a very high frequent way from the managed system. So this can have a big impact on the architecture. So all the scenarios are defined, and for each of the scenarios, quality of service goals are defined. For example, as you see, the quality of service goals of the IoT system can be that energy consumed should not be more than 10 joules in 10 minutes. On the other hand, for the managed system, it can be that the analyze activity should not take more than 0.05 seconds for the complete analysis. From these scenarios, the most critical scenarios are identified, and these will form the top scenarios. So this will be also decided considering the functional and non-functional requirements of the system. Now, once the top scenarios are selected, the next step is to define the architectural strategies for implementation. So the system design process takes into consideration the top scenarios along with the quality of service goals to generate architectural strategies, or rather candidate architectural strategies. So generating architectural strategies implies defining components of the managing system, their connectors, and the corresponding behavior. As I've explained in the previous slides, we consider the MAPK framework for implementing the managing system. So which means that 5 different components exist. Now, each of the components can be implemented using different technologies. They may be connected to each other using different mechanisms or different connectors. The technology choice for component implementation, type of connectors, and the associated behavior can result in different type of candidate architectural strategies. Once these strategies are selected, each strategy is used to create a managing system, and they are integrated with the IoT system to generate a working prototype of the IoT system. So in this work, we specifically take into consideration three strategies. The first one is centralized connector. In this strategy, there will be a central component with which all the components of the managing system communicate as depicted in the figure. The central component also serves as the knowledge base. The knowledge acts as the connector component between the different components. So basically, they all interact with each other through the knowledge, very similar to the Blackboard style implementation. The centralized connector can be implemented in different ways. For example, through an in-house database, a cloud database, or even a centralized file system for that matter. Now, the second strategy is very similar to a pure event-driven architecture. So each of the components communicates with each other through a message broker. So essentially, they use a publish-subscribe pattern where each component publishes an event to a topic, and the next component can subscribe to the topic for consumption. So as compared to a centralized connector, here each component do not communicate using the knowledge component, rather through the message broker. As we can see in the figure, there is a topic that allows unidirectional communication between each of the four components from monitor to executor. In addition, they also communicate with the knowledge using dedicated channels. The architecture and the number of these topics will change according to the implementation strategies. For instance, just one topic would be used for all the communication between the main components, or one topic per component could also be employed. Now, the final strategy that we consider is the socket-based connector, which is more or less similar to a layered approach. In this case, the MAPE components are all connected through a TCP-based socket connections. The flow is very similar to the previous one. The difference, however, is that this time the communication between all the components is achieved through a TCP connection using sockets. Now, that brings us to the third stage of the framework, which is the analysis. So once the candidate architectural strategies are defined and selected, the main task then is to analyze to see what are the cost and benefits they provide. As explained previously, once all the strategies have been defined, they are composed to generate system prototypes. Now, these prototypes are first simulated using available IoT simulation tools. For instance, Cup Carbon could be used to simulate an IoT system, or AWS IoT simulator could be used, and so on. During the simulation of the IoT system, the managing system is executed to perform the adaptation. So once the simulation is done, the results are generated in the form of logs and they are collected. So both the execution logs of the managed system as well as that of the managing system are collected. These logs are then processed by the utility analysis process to perform cost benefit analysis following the CBAM approach. For example, the quality of service of the managing system can be considered as the cost. For instance, the response time of each of the MAPE activities, that can be considered as the cost, and the energy saved by the IoT system can be considered as the benefit. This process is repeated for each of the generated prototype. Now let us look at this cost benefit analysis in detail. So this steps allows the architect to analyze the total utility in terms of cost incurred for the implementation of a given strategy. This cost can be the economic cost that has to be incurred for implementing a strategy, or in terms of the quality of service of the components. While CBAM uses a manual analysis, we use an automated approach using a cost utility function to calculate the overall cost. So from the execution logs of the managing system, the quality of service data is generated. We perform an aggregation on it, and then the data is normalized. For example, as stated in the previous slide, let us assume that response time is the parameter for calculating the cost. Then for each architectural strategy, at any adaptation interval tau, we calculate the cost using this utility function. Of course, I'm not going into details of it, but this utility function gives the overall cost of using a strategy for a particular adaptation interval tau. Similarly, then we compute the benefit in terms of the quality of service goals of the managed system. So this step also takes an automated approach as in the previous case, and it uses a benefit utility function. This function is applied to the quality of service values obtained from the logs of the IoT system. So in this work, we want to reduce the energy consumed by IoT system. Hence, we consider the energy saved by the IoT system as the benefit. So if you consider, let Emax denote the maximum energy that can be consumed by the IoT system for a given adaptation interval, then the benefit accrued by the IoT system while using a given architectural strategy for the implementation of the managing system is obtained by computing the utility function, which is actually a piecewise function. So once the cost and benefits are calculated for each strategy for every adaptation interval tau, the final stage is to evaluate the different strategies. This is achieved using the ROI evaluation process. So it computes the return of investment for each of the architectural strategy. It computes the sum of the ratio of the cost incurred by the managing system when using an architectural strategy with respect to the benefit provided by the implementation of an architectural strategy on the IoT system. So the architectural strategy that provides the highest ROI can be used for implementing the managing system for a given scenario. In addition, the framework also provides flexibility to the architects to easily refine or modify the strategies by going back to the previous stages, modify the quality of service goals, redefine parameters, rerun the analysis and the evaluation stages. In this manner, architects can quickly and systematically evaluate different strategies for implementation of the managing system. Now, the most important part is to see the impact of using the framework proposed. To this end, we evaluated our approach with the help of a Microsoft Azure instance. We made use of CupCarbon IoT simulator to simulate the NDR IoT system by taking into consideration observations from the real case study. As for the experimental candidates, we made use of two different scenarios, one which takes into consideration the regular hours of NDR. We performed the simulation for 24 hours with an adaptation interval of 60 seconds, which implies that every 60 seconds, the managing system will execute the MAPE loop. The second scenario was simulated for 2 hours, where every 1 second the MAPE key is executed. So this kind of simulates the peak hours of NDR. We made use of 4 evaluation metrics as defined here, 2 of them which focus on average response time and average energy consumed. Then we also considered cumulative cost, cumulative benefit, and cumulative ROI incurred by each of the architectural strategy as other evaluation metrics. And by the way, we used Python for implementation mostly, and MySQL for the centralized connector, Kafka for the message broker, and traditional socket library in Python for the TCP socket-based approach. Now, the main goal of the evaluation is not to show which is the optimal choice, but rather to show how the framework can be leveraged to evaluate different architectural strategies based on different scenarios and corresponding thresholds, like quality of service thresholds. So the plots here shows the accumulated ROI while using 3 architectural strategies for the 2 different scenarios. You can see that the threshold that we have used in these scenarios, with scenario 1, we observed that centralized connector emerged as the optimal strategy. The main reason was because we had used MySQL and the time taken to read and write were much lesser compared to a socket connection or using a message broker, as opposite to a contrary, as contrary to a popular belief. In the second scenario, with an adaptation interval of 1 second, socket performed the best compared to publish, subscribe, and centralized connector. So initially, we can observe that all were giving kind of similar ROI, but as time progressed, we can see the gap between the architectural strategies of the socket connector and that others starts increasing. So we noticed that average response time of the managing system was very less when using socket-based connector. This also meant that the adaptation done were more effective, allowing more reduction of energy consumed by the IoT devices. Now, this gives a more detailed view. This table shows the results of analyzing different strategies for the 2 scenarios. In each of the strategies, we used 3 different thresholds to find the most optimal architectural strategy for the given scenarios across different thresholds. Just to emphasize, this cost is with respect to the average response time and benefit is with respect to the energy consumed. As it turns out, you can see that in scenario 1, socket performed the best when we were using the default thresholds of 0.06 and 15. But when we changed it to a different value, we observed that when we were using a different threshold, we could obtain a higher ROI for socket. But apart from that, in most of the cases, centralized was performing in the optimal manner. So you can see that when you change the threshold, different architectural strategies performs better than the other. Similarly, for scenario 2, we observed that in all the cases, socket performed the best. So even with respect to response time and energy consumed, it was the most optimal, which gave rise to the highest ROI. So similarly, this kind of approach demonstrates that when you are using this kind of frameworks based on the goals and scenarios, different implementation strategies can be simulated and can be tested systematically to identify an optimal choice. Of course, there is no one solution for all the scenarios. So it is all about identifying the one based on the given goals. So to conclude, we have presented a framework to systematically evaluate the implementation architectures for managing system. We found out that quality of service goals and scenarios can have a big impact on the choice of implementation. We also observed that the way you implement the managing system can have an impact on the quality of service of the underlying software. So future works include generalizing the approach to other class of software systems. We also plan to incorporate sustainability framework to perform cost benefit analysis while performing adaptation. And we want to evolve this framework into a tool. So hope you enjoyed the presentation, and we'll be happy to take questions.